In this video, I'm going to talk to you about what a z-score is, why we might even care to use one, and also then build on that to be thinking about the normal model and its importance in a lot of statistics, especially whenever we start talking about inferential tests and that sort of thing. So I hope this video is helpful for you. So I'm going to go back to this data set with raisins that you might remember from a previous video. And the reason is because this raisins data set has some nice different distributions to look at, different shapes. And so if you remember, there was data in this data set about people who were predicting how many raisins there might be in a box of raisins. And then there was the actual number of raisins in a box. And so for now, we're going to focus on the predicted number of raisins per box, largely because it's skewed and it makes it a little more interesting to look at. And I think it helps us, begs the question, how different are some of these values? So for instance, if we look at the predicted values, if we just look at the dot plot for a minute, this point over here on the far right at 150 sticks out a lot. And so you might be thinking like, wow, that seems really big. It looks like it's far away. And there's different ways we could quantify how far away that actually is. And if you didn't actually see the distribution, then you might think like, well, I don't know what size boxes of raisins these were, so maybe the value 150 makes sense if somebody's talking about it and brings it up. Or you might be thinking, well, maybe that is really big, and there's different ways to be approaching this to think about how big is the difference that we see. And so that's really the question I want to focus on for now. How big is the difference that we see? So if we go to this page here, I think we can do some calculations. So I've added this little box at the bottom. So another way to ask how far away is 150 from what might be the typical prediction could be how unusual is a prediction of 150. I mean, we can see it here. It looks pretty unusual just by seeing how large the gap is, how far away it is from these values that are down here in the 20s and 30s. So it looks really large. But how unusual is it? Well, one thing we might do first is just say, well, how far away is it from the mean? And in this case, we could just simply subtract 150 minus the mean of the predicted scores. And we get 117. Okay, that's pretty far away. But then we might think, well, maybe it's really far away, or maybe it's not, if we didn't actually see this picture, right? So a way to quantify that is to first think about, well, what is the standard deviation? How much spread is there? So we could take the standard deviation of the predicted values, and we get a value of 23. So if we're thinking about this being 117 more than the mean, this 150 is 117 larger than the mean, then if the standard deviation is 23, and remember the standard deviation is saying like this is the average distance points are from the mean. So we could say, well, if the standard deviation is 23, how many of those might that be away? Because this is the standard distance that things are from the mean, right? So for instance, if we come up here to this plot, and if you've seen, there's a video I make with Tinkerplots. If you've never played with Tinkerplots, or the browser-based version of that called CodeApp, it adds these bars and it shows you the range of the standard deviation, which is really nice to see. And we can add some movable lines here. Um, and let's just put one. So the mean, actually, what is the mean? We need to find the mean first, right? The mean of the predicted value is about 32. So let's put that at 32. So here's the mean. And then if we add another one, and let's say we put that at 23 above 32, which would be 55. So this is one standard deviation above the mean between these two lines. And then we could add another one and go below the mean too, right? So if we go 23 below 32, that puts us at about 9, right? And I don't know why it's going to decimal points here, but we'll get it as close as we can. Let's say 8.9, sure. Okay. So, we see this is the distance below the mean. So, and you can see the majority of the data is in this range of one standard deviation. Well, how many of those away is 150? If that's the standard deviation, the standard difference that things are away from the mean, or the average distance from the mean, how many of those do we have to go away from the mean, which is this line right here, to get to this 150? So as we're thinking about this, we might think, okay, well, we could count this, right? And we could count another 23 and another 23 and another 23 until we see how far away 150 is. And that would get us pretty close. But we can use math to figure this out. So first, we need to know how far away it is, and then we need to know how many of those is it away. So I'm going to take you back to thinking about division for a second. So first, I want you to just think in your head, what does it mean when I say 6 divided by 3? Bear with me here. One conceptual way to think about this 6 divided by 3 is to say, well, that means how many groups of 3 are there in 6? Which, 6 divided by 3 is 2, because there's 2 groups of 3. So another way to think about this distance here is to say, well, how many groups of one standard deviation, in this case 23, are there, and how far away this is from the mean? So, and we figured out the distance from the mean was 117. So how many groups of 23 are there in 117? How many distances of 23 do we have to travel to get to 117? So that's the division that we need to do. How many standard distances from the mean, or standard deviations from the mean, is 150? And to do that, we simply divide. So we need this at the top. This is the distance that 150 is from the mean. And we're going to divide by the standard deviation, because that tells us how many times can we move one standard deviation before we get to 150, if we start counting at the mean, right? And if we calculate this, we get 5. So we might be thinking, okay, well, like how big is 5? Is that actually big? I'm going to put a line here at 150. So this is 5 away. So is that large? It looks large, but is it large? And one way we could think about it is, well, how far away is 80? Because that's right here, right? I mean, how far away is that? And we could calculate the same thing, and this time instead of putting 150 in there, we can put 80 in there. How many times can we move a distance of 23 before we get to 180? And we get about 2. So if we come up here, we can add another line here at 80, and that's 2 away. So this is 1 distance away. This is 2 away. This is 5. That's quite a big difference to go from 2 to 5 away, especially since there's really not much in between here. I mean, if we went 3 standard deviations away, there would basically be nothing between 3 and 5, right? And then we could think about another one. So there's this one student who thought there would only be 1 raisin in the box. And so that's unusual to guess that amount, just like it might be unusual to guess 150. And then we could ask, well, how unusual is a guess of 1? And one way that we can decipher that is to ask how many standard deviations away from the mean is it? Is it far away? Is it close? And if we calculate this, and of course, before I show it to you, it looks closer, right? If the mean is somewhere in here. And we get negative 1.3. Why is it negative? Well, because we have a value that's less than the mean. So we're subtracting 1 minus a value larger than 1. So the negative just means it's less than the mean. So if we come back up here, we can add a line just to help us keep track. And that's going to be here at 1. If I can get it to land on 1. Close enough. Okay. So we have a distance of a little more than 1 below the mean for a guess of 1. And the guess of 150 is 5 standard deviations above the mean. And these distances from the mean, or numbers of standard deviations away from the mean, these are called z-scores. And they're really important because they can be comparable across groups of people and across distributions. So, for instance, a distance of 5 away from the mean is always going to feel large, far away from the mean compared to everything else. Whereas a distance of 1 away from the mean, or maybe even 2, seems like it's fairly close compared to everything else. Especially if we go out farther than 5, then it feels even closer, right? But in this case, 1 or 2, within 1 or 2 standard deviations away, seems like we're capturing a good amount of data. And if you look at this, within 1 standard deviation, that's the majority of the data already, right? Over half of it for sure. And then once we go out to 2 standard deviations away, now we've captured the overwhelming majority of the data. Okay, so that's z-scores, and they're important because they help us identify things that are far away and compare things to each other in terms of how far they are away from the center. So now that we've thought about that a little bit, let's actually create that z-score. So here I've already gone ahead and calculated it, but if we just put this in, we can say take the predicted value, which is in this column A here, subtract the mean of the predicted value, and divide by the standard deviation of the predicted value. And when you do that, you get this list of numbers here. Whoops. And then we can plot these. And on the next page, I've created a plot of both the predicted and the z-scores of the predicted. And one thing you'll notice is that the plots look identical. The distributions look the same. They have the same shape. And if we put them next to each other like this, You can't tell the difference which one is which unless you look at the scales at the bottom. So it doesn't change the way that the distribution looks, and it doesn't change the relative distances between points or across these points. Okay, so that's the nice thing about changing it to a z-score, which is also called standardized scores, because it's in terms of standard deviations from the mean. How many standard deviations is everything from the mean? And of course, 0 represents the mean, because if this is the distance from the mean, 0 means the point is 0 distances from the mean, which means it is the mean if it's a distance of 0 from itself. And that can help us identify up here that the mean is in here, 32. Okay. All right. So as we look at these, we can then start to identify like, oh, this point is about 5 standard deviations away, like we calculated. This point 80 is about 2 standard deviations above the mean. And then, of course, we have this point that's a 1 here. The value of 1, which is a negative 1.3 away from the mean, or 1.3 below the mean. And so I think that's hopefully helpful for you to see these next to each other, that they don't change shape. They just change the meaning of the value so that you can compare how far away things are more directly. And notice that there's no units on it anymore. So up here with the predicted values, these are numbers of raisins, 150 raisins. But this doesn't really have a unit anymore. This 5 doesn't represent 5 raisins. It just means 5 standard deviations away from the mean. In that case, above the mean, because it's positive. Okay, so why should I care about this? Well, especially when we're thinking about statistics, we want to know how far away things are, and it helps us. If you've seen my other video about central limit theorem, it also can help you in thinking about an initial understanding of p-value. But it helps us identify outliers. It helps us identify whether two groups are different from one another, or two individuals might be different from one another by looking at these values, and being able to compare them on a more standardized measure where maybe the values might be a little bit different between two groups. It also is helpful in thinking about the normal model. And the reason we care about the normal model is that a lot of things in statistics are built around that concept. And there's a lot of things in the real world that naturally approximate a normal model. And a normal model looks like this. And don't worry about the details of this at the moment, but it's a symmetric shape. You can see if we look at the center here, the left and the right are mirror images of one another. And it has a mean of 0, which because it's symmetric, the median is 0 and the mode is 0. And it has a standard deviation of 1. And it has some interesting features to it that we'll talk about in a little bit. But first, I want to go back to thinking about raisins. And for now, I want us to now focus on the actual number of raisins. So first, let's go ahead and create z-scores for these raisins. So if we take the actual number of raisins and subtract the mean of the actual number of raisins and divide by the standard deviation of the actual number of raisins, then we get the z-scores. So we've standardized the values. Okay, we'll want to use that here in a moment. But first, I want to come and let's plot the actual number of raisins. So if we look at the actual number of raisins, the distribution looks a little different than it did for the predicted, right? The predicted number of raisins is highly skewed to the right, whereas here it's not so much. And it might be more helpful even to turn this into a histogram and see it looks more like a symmetric shape than the other one did, but it does look a little bit skewed to the left, with a center somewhere in this range here. So, and I've got down here the standard deviation to help us think about this. The standard deviation is about 3. So if we change this to the z-scores, it might help to see this. And I'm going to change the bin widths here a little bit. There, that's better. Just to close the gaps a little bit. All right, so a standard deviation of 3. So if we remember, here is the mean, 0, because we're looking at z-scores. So from there to 1, this 1 represents 1 standard deviation. So that's a difference of 3, about 3 raisins difference. So half a standard deviation is going to be about 1.5 raisins, which doesn't make much sense, right? But that's the way you can interpret it if you know what these values are. So it looks still kind of skewed. And it would be nice if it were not, because then we could think more about what this is going to look like, and how close it might be to a normal distribution. And we can actually add a normal model on top of this. So if this were normally distributed, this is what it would look like. So you can tell these bars here are too tall. This bar over here is too tall. It should be shorter. This bar here is not quite tall enough. So some of these over here would need to shift. And once we were able to do that, though, because it's a mirror image, there are some things that are always going to be true with these kinds of models. With those kinds of models, within 1 standard deviation, in this middle proportion here, contains about 68% of all of the data is within that range of plus or minus 1 standard deviation. So here, that would be about from -1 to 1, although we'd have to shift a little bit to the right, because these points are a little bit off. And that would contain about that amount of data. And if we went out to 2 standard deviations away from the mean, this little Greek symbol sigma means standard deviations. So if we move out 2 standard deviations, expanding along this arrow here, we get about 95% of all the data will fall within that range if it is normally distributed. And then within 3 is 99.7%, about. These are not perfect values. They're just approximate values that are helpful to remember. And that's why people call it the 68, 95, 99.7 rule. And it's a rule of thumb. It's not perfect, but it's very close to this value or amount. And of course, in the real world, nothing is going to be perfect normal model. That just doesn't happen in the real world. So this is a theoretical model, right? But things do look like this a lot in the real world. So it is helpful because we can make these approximations and get a perspective of the data without having to do as much calculating like we would have to do if it were a skewed distribution like this. That rule is not going to hold. We're not going to see necessarily 68% of the data within plus or minus 1 standard deviation. Okay, and this is really helpful for talking about things later that have to do with statistical tests that make assumptions that things look like this shape. So it is an important thing to make sense of and to be able to spot whether this is the case or not. So I hope you found this video helpful, and let me know how your thinking is about this in the comments.